Good morning, students. Welcome to the mass transfer course. Today will be lecture 22. Here we are discussing about the gas liquid contacting equipments. In the last day, we have seen that for gas liquid, mainly two equipments are widely used in industry. These are pack tower or pack bed and tray column or plate column. Today we'll discuss more about these two equipments. Let's take the first one, that is plate column or tray column. So plate column, yes, last day I told that there will be feed. Okay. It feed can be bottom or it can be in between also, it depending on the feed quality. Feed quality means if feed is mixture of liquid and vapor, then for that one feed will be little bit higher, because whatever liquid part is there you need to evaporate, and for this one there will be reboiler of heating material, and this part will be your stripping section, and this part will be rectification section, because here more volatile component will come as a top product. So we'll get the whatever the top product will come, the purity of this more volatile component will be high, and at the bottom we'll get the less volatile component in high proportion. And what we told, that reflux is given, it is part of your top product, the top tray, and this is the tray. So in tray a liquid we are filling, and these are the holes here, gas are moving and liquid is moving through this direction, then through this downcomer it is coming to the next plate, where then liquid is moving in this direction, and again it is like this cross current type of liquid movement is there, and gas is flowing through this trace. And if you see this thing in little bit other way, so if you see that your gas flow rate, okay, there will be froth will be there will be gas will carry out some liquid part, okay, which is moving in these directions, and liquid is coming, if you see it is coming like this. And here one of the key thing is here your tray. In tray, this is the valves will be there, okay, the valves will be that is the other thing, this is the main component of the plate column. So if I consider a plate or tray column, it consists of mainly four parts. First one is cell. So this is the cell. This one the cell. So and you in your next semester onwards there will be two lab courses: equipment design and drawing 1 and equipment design and drawing 2. There you will able to determine what is the thickness of the cell, depending on the particular chemicals used, particular pressure, what will be the thickness of this the cell, and what will be the material of construction, that you will learn in detail that time. Okay, next semester there is, if you see, process equipment design and drawing 1 and drawing 2, two lab courses. But here we are mainly give the one overview Okay, and how the process is going. So one first thing is cell. Detailed mechanical design of a cell you will learn in this lab course. Then another main component is tray. Okay, this is the tray, and third thing is this is called wire, and this is the downcomer. Okay. So cell, trays, downcomers and wire, and there will be different nozzles. These are the mainly four parts in a plate or tray. Now let's go one by one. Cell. Cell is usually made of metal or alloy. The metal is selected on the basis of corrosiveness of the fluids, temperature, pressure conditions, and the cost. Sometimes plastic are also used nowadays. As I told, what will be the material of construction of the cell, what will be its thickness, and what will be cost, that you will learn in detail in process equipment design 1, drawing design and 1 and 2. There are 2 lab courses next probably 6-7 semester. So that you will, and in general the diameter is 1 meter to 10 meter. You understand, 1 meter means 3 feet around. Okay, so 3 feet diameter, it's a more small plate column minimum. 10 meter mean you understand 30 feet diameter. It's huge. Generally in petroleum industry, okay, there where huge flow rates are there is people are using the diameter around 10. But when you need the flow rates are less, then we'll get one diameter 1. So this is the typical range in industry use, and we'll later in this chapter we'll learn how to determine the tower diameter. That also we'll do it here in detail. So cell thickness is generally calculated using standard vessel design code. Okay, so that I told from this lab course you will get this thing. Cell is generally fabricated based on the design, because it is very important, means cell is generally fabricated based on the design. That's mean one cell you will not get in ready-made way. Just like you are getting the half-inch pipe, 2-inch pipe, 3-inch pipe like this, but cell you will not get in market because it is rare equipment depending on a particular process. Okay, and this is design, because you are the chemical engineer, you will tell the company, okay, I need the cell of this diameter with this material and what will be this thickness. Then it will be fabricated from the construction company. Now tray has 2 major functions. What it allows the gas to flow through the holes. The gas vigorously bubbles through the liquid to form a gas liquid dispersion. The tray holds the dispersion on it. You understand? So tray means from the bottom the liquid hold up will be there, and from the bottom gas will bubble, so there will be gas liquid vigorous mixing. The trays separate the column into a number of components, each of which constitute a stage. Mass transfer between 2 phases occurs on a tray. Therefore, the tray as a whole constitutes the heart of the column. The performance of column depends upon the performance of the tray. So you understand, the tray is the major part of the plate column. If you can design one efficient tray, then you will get the better separation. Now, how does it look like? Here I am generally there are three types. One is sieve tray, one is bubble cap trays, and another is valve tray. Now you see I told this is a circular disc. Yes, this is the valve tray. So this is a circular tube. So one plate is there. Okay. So here from the top liquid is coming here. Okay. Then what will happen? Liquid will come to this area. But this part it will be set to your cell, so no liquid come down from these are areas from the outside area, isn't it? So when this plate will be fit to a particular cell, okay, then this circular outside periphery, this part will be blocked. So liquid is coming from the, let's take from top to this area, then it will flow here. Okay, so these are wire. So it is flowing here coming, and then from the bottom there will be holes. This is called holes. Small holes are there. So the gas is coming from the bottom. So there will be, and this will be liquid hold up. How much up to this? This is called air. Okay. So air, then it will come down to the next tray through this hole. So if you see, this is the thing, 3 dimensional, it will come to the next. So it is come next tray. The next tray will be just opposite way. So again this tray, this side will be here in next tray, and then liquid will flow this way. Then this side will be here. It will be like this. So this is the simplest configuration of the sieve. Sieve means what is nothing but there are small holes, and the liquid hold up will be up to the height of this wire, and this is called downcomer. So if you see, if you have a tray like sieve tray like of thing, then your gas flow rate is 0. Let's say only liquid flow rate is there. If gas flow rate is 0, then all the liquid will come and it will come down through these holes. Nothing will come here, isn't it? Because, but if you keep increasing, liquid flow is there, keep increasing gas flow rate, then there will be one situation will come when gas will come from the bottom and it will mix with this liquid, and the mass transfer will happen from gas and liquid. And after a particular velocity, no liquid will come down, because that whatever the gas pressure is coming, if this is higher than your liquid hold up pressure, then liquid cannot come down, isn't it? So this is the sieve. Now you understand here the problem is you have to keep the gas flow rate for to a one threshold value, so that no liquid should come within the holes. But if gas flow rate is low, then liquid will weep. Okay, and if gas flow rate is very low, then liquid will dump. Weep means it will come slowly, drop by drop. But liquid, if gas flow rate is almost 0 or very low, then liquid will dump. It will be continuous liquid will flow. Okay. So this is the valve tray. Now, if in this tray, if gas flow rate is too high, then what will happen? If gas flow rate is too high, then the pressure drop will be also high. Then what is the pressure drop between two trays? If higher than the liquid holder, then liquid will move here upward. It will, instead of coming down, it will go up, because here high pressure, here it will be low pressure up. If pressure drop is very high, if gas flow rate high, and then slowly liquid will fill up this column, and this is called flooding condition. Okay, so if gas flow rate is very low and liquid flow rate is very high, then dumping and weeping will occur. But if liquid flow rate is okay and gas flow rate is very high, then the column will flood with the liquid because of this, whatever the pressure drop between two consecutive trays, if it is higher than that pressure drop higher than the liquid hold up, okay, or liquid here, then liquid will go up and slowly it will fill the column. So this is one shift, and there is, you understand, there is some problem. Now people try to modify this. So instead of shift, so you can understand here liquid will come from the top and it will flow through. This is the tray, okay, gaps, okay, and then liquid will come down here. This is the way. So this is called the bubble cup. Bubble cup means I will show you the one different next picture. What is its construction? In this way, we restrict the liquid dumping or liquid weeping up to a certain level. A liquid will cannot come a particular, means this tray cannot be dry. Dry means no liquid. If it is gas is very low, then all liquid will come down. That means there won't be any liquid particular. So then there won't be any gas liquid mixture. So to restrict this arrangement will restrict, there will be some liquid hold up, and that weeping and dumping can be minimized. And there are valve tray came. Okay, valve tray, in valve tray it is designed in such a way so that there won't be any weeping or dump, whatever the gas flow rate. If gas flow rate is 0, okay, but no, then valve will come designed in such a way it will allow only to come the gas from the bottom, it will not allow any liquid from the top. So always there will be in the tray, okay, in the tray there will always liquid. So it is the better, sometimes if you see, if you consider the practical situation of a equipment, okay, operation of a tray column. So sometimes in industry there will be some pump is not working, pumps are also, then there will be gas flow rate maybe the 0 for let's say half an hour or 10 minutes. Then what will happen? If we have a sieve tray, all liquid will come down, and then again when gas will come, and to make it will take time. But if you has a like this if I use the valve cap, then what will happen? If gas flow rate is 0, sometimes for some emergency purpose, it's okay. Then gas will be, but liquid hold up will be there in the column. Then once you will start the gas flow again, that it will come to the steady state very fast. So this is the modification. These are the modification are made. Now I told that sieve tray is nothing but a hole, small hole. The gas flow rate, that flow rate of the gas will be so high, so that it will push this liquid ahead, and it will come, and there will be both. And generally holes are generally 1/8 inch to ½ inch diameter. This is the thing, depending on what gas flow rate will be there. Okay. Here if you keep the holes higher, then advantage is there will be low pressure drop, but liquid dumping probability will be high. Okay. So here you can consider it is nothing but a hole, okay, and gas will move here, it will bubble through this, and actually the mass transfer happening within this tray. So liquid is coming, so gas there is the bubble, liquid, their mixing is going on, and then it is coming down. going up, gas is going up, and liquid is coming down to the next. So this is the sieve tray. Then if you take the bubble cap design is like this. So this is actually one. You take one circular. This is actually, this hole is circular hole. Okay, this is circular hole, and there is one circular ring above this. Okay, and then it is, and above there is a cap is there. So, and as this is like up to this, and gas will move from here to there, here, and then it will come, and here this will be high flow rate, small area. So high flow rate, the liquid come down to this area will be less. Now if the flow rate also even 0, then what will happen? Some liquid will, whatever the, if tray has a, let's take up to this height, then some up to this height liquid will down, but after that this much liquid will hold up by this tray. So there is, this is the better advantage. But here the problem is, as gas is taking this path, the pressure drop is high compared to your sieve tray. So this is the 3 dimension, and this is the, but it is fixed. So sieve tray and bubble cap, these two, that whatever the area, this cup area, this is fixed. In this case this is the thing, and in this case whatever the hole, this is the, so this is the fixed area. Okay, but here still there is some problem. Then the next design came with the valve tray. What is valve tray? It is very easy. So this is one valve, this is the cylinder, circular, okay, plate is there. With these two extended part, it is tag here. So if, let's take, if this is like upside liquid, this is the tray, one, this is one valve. So when liquid, let's take gas flow rate is 0, so then what will, this valve will come down. Then it will fix it here, this top part, and then no liquid, it will not allow any liquid to come down. Now if you increase the, let's say, vapor flow rate or gas flow rate, then according to whatever the pressure of this vessel, it will move up. So if it is moving up, then this area is increasing, that what is the flow area is increasing with them, and the maximum it can, this part can come here. The flow rate normal, low, if it is very high, so up to this it will, but that's when valve is here variable. Valve here, flow rate valve is allowing the flow area in a variable, and maximum will be here. When it will stuck to here, then after that no area will be available. But up these to this, okay, so here flow area is variable. But here advantage is that whatever the your gas flow rate, it does not matter, liquid, the dumping or liquid weeping will not go. Okay, so these are, but you understand, on sieve tray, construction of a sieve tray, it's very easy. You just make a hole. Valve tray is costly because not so many parts, but valve tray is easily better than this. Okay, so this is the variable area. So closed position, this is open position, and these are the construction of valve tray. So if you take the comparison, bubble cap capacity of column medium to high, it is okay. It is high to very high. Valve tray, okay, valve tray means only the sieve is there, sieve tray. Valve tray is high to very high, and sieve tray also high. Whatever the capacity, it can take. Efficiency medium to high, this is high, this is high. Efficiency in these two trays are high. Pressure drop in valve tray high, This is medium to high, this is medium. You understand why this is bubble cap? Because if they are taking one zigzag path. That's why they have pressure drop is high, and valve tray medium to, and sieve tray is lowest pressure. Entrainment 3 times than the sieve tray. This is medium and this is medium, but that's mean entrainment in valve tray is high, because the flow area is low, so when it is coming, it is more entrainment is there. Okay. And turn down ratio, I am telling this what is the turn down ratio. This is excellent bubble cap, 4 to 10.1. This is 2.1. Cost 100 to 200% more than the sieve tray, because that's whole of this, and this is 20 to 50% more than the sieve tray. So cost of bubble cap is greater than the valve tray. Okay, and this is the cheapest because this is the what is the turn also. Design vapor throughput. What is the design vapor throughput and minimum operable throughput? What is the design vapor? Whatever the design flow rate of the vapor, and what is the minimum I can make? And you can understand in this case sieve tray, it is the worst 2.1. If you keep the flow rate, minimum flow rate, you cannot go beyond certain value, because then wiping and dumping will come down. And valve tray also, it is, if it is far better, it is also. Okay. So in market share, you understand that sieve tray is the easiest and cost cheapest one. So where the company does not have a much constraint on whipping and dumping, means when their gas flow rate will not fluctuate much, they can go for sieve tray. And bubble cap is the worst. Share market bubble cap is 5% because disadvantage it is, isn't it? Because cost is higher, entrainment is higher, and capacity also not so high. Okay, and pressure drop also high. Pressure drop is very important. You are losing the energy. So bubble cap in industry, if you take the share per weight 5%, sieve tray is 25%, and valve tray is 70%. Okay, this is so there are 3 types of valves are there: sieve tray, bubble cap, and valve tray. And in plant plate design, the tower diameter in general, when diameter is 1 or less, means if tower diameter is vessel diameter or cell diameter is 1 meter, 1 meter means 3 feet or less, then it is around 500 or between 150 to 500. So if you take the average, this is around 300 millimeter. 300 millimeter means 30 centimeter. 30 centimeter is equal to almost 1 feet. So when diameter is around 1 meter or less, okay, so generally 1 feet is its tray facing. Tray facing means the what is the gap between 2 trays. Okay, so if you take this is this is one tray, this is another tray, this is gap between 2 trays. Okay, so if you have this 1 meter, that will be, but sometimes column diameter may be less, so it is around minimum will be 300, 1 feet trays. Then 1 to 3 600. 600 means if column diameter is 1 to 3 meter, then it is 600. 600 means around 2 feet. Tray spacing will be 2 feet. And 3 to 4 meter diameter, then 750 means 2.5 feet. And 4 to 8, generally 900 millimeter means it is around 3 feet. So depending on the column diameter, the tray spacing, it is the typical industrial data. It is experienced people are using this one. So generally tray spacing, that's why I am telling general column diameter is around 1 to 10 meter and tray spacing between 1 feet to 3 feet. And it depends on the diameter of the column. Later in this course, in this chapter, we will calculate for a particular system what should be the diameter. So once you will get the diameter of the column, so then easily you can, from this chart, you can easily calculate the what will be the tray spacing. Okay, and from your mass transfer theory, if you can calculate number of stages, okay, let's take 30 number of stages is there, and if you have a stage spacing, let's take 900, then your column height will be 1 meter into 30 means 30 meter long, and we will get the what will be diameter of the column. That's mean we have designed the mass transfer equipment. We know the what is the diameter, we know what will be the height, and we know what is the tray spacing. So then other things are mechanical, but you have to fabricate according to this thing. Okay. Now this is for things downcomers. Okay, so you understand this is the tray is coming. So this is the wire to hold up this liquid, and this is the downcomer. And if you instead of straight, if you make it bent, okay, then it will be better. You know, liquid will flow like this. Okay. Sometimes when fluid is high, this is the but it is cross current. But sometimes it will come down from the, let's say, top tray. It is coming like this. Then this tray is there, okay, and in the middle there will be one hole. So downcomer will be in the middle, and these are the wires. Okay, so downcomer middle. Then next tray is like this. Then it is coming to like this. This type of tray spacing is also possible. Okay, and downcomer like generally when diameter is high, then liquid flow rate will be like this. Then because 10 meter diameter going fluid one to other place. Now instead of doing that, if you make it like this, then it has been seen that mass transfer are much higher because there will be uniform mix. Okay. So I am downcomer and wires and nozzles, Now this is one interesting point already I discussed. Let's take this is the column, okay, and tray. This is the vapor velocity, this is the liquid velocity. Let's take gas velocity is low. Here this line means gas velocity is low and liquid velocity is high. Okay. So if gas velocity is low, liquid velocity, then weeping will happen. And when gas velocity is very low, then dumping will happen. Now if you say liquid velocity is low and gas velocity is high, if you increase this gas velocity, then slowly what will happen? Entrainment will be higher. Entrainment means gas will carry the liquid droplets, and if the gas flow rate is very high, liquid flow rate is very low, then what will happen? It just blowing will happen, means it is entering from the bottom, okay, it will enter from the bottom and it will directly one channel type of thing will go directly from, because gas flow rate, so liquid will, there won't be any bubble formation. Instead of bubble formation, there will be blowing, means there will be one channel of gas, so it will go up. So then if it is like this, then there will be no mix, no mass transfer. But let's take liquid flow rate is high and gas flow rate is also very high. Gas flow rate also very high. Then flooding will happen. already I discussed that if gas flow rate is very high, then what will happen, that what is the, then if gas flow rate is very high, then pressure drop will be high, and if the pressure drop between two trays is higher than the liquid head, then liquid will move to the upward instead of going down, because higher tray has a lower pressure than the lower trays. So liquid will start move upward instead of going down, and then slowly the whole column will be flooded. This is the, and phase margin and liquid. These are the thing, and this thing. Now you cannot go either of these, so you have to keep the flow rate in such satisfactory operation. So you should not go flooding, blowing, entrainment, damping, whipping, all these things. So UT will be this, and if you keep this hand high, very high, then there will be phase margin, means no phase will be distributed, it will just go like this. So your column operating zone is there. This is the satisfactory operating. So this is the another way picture where you are doing this thing. Now let's do the packed tower. Packed tower is cell. Already I discussed. It is very similar to that tray tower. Okay, packing material we'll discuss it in detail. Then packing support and gas distributor. This is the support and this is the gas distributor. You know, this is the simple thing. Liquid collector and liquid distributor. It is also and demister or entrainment element. This is the demister. This is nothing but a small hole where if there is some liquid entrainment gas will carry the liquid droplet, then that will resist to come upward. So these are the five things, but these three are easy. Cell already we have discussed. So another thing we will discuss with the packing material, and thing is the why I am discussing here. My aim is I will use this packing material in such a way so that I will get the higher surface area for the masters. So type of packing, okay, this is the packing. So packing material, this is the packing material. It is structured packing. I will come down. Then this is your packing support. It looks like this, okay, and this is the liquid distributor, okay, and there will be random pipe. So if you take the three-dimensional view, this will be like this. So this is one packing material, packed bed part. Then because they don't want to continue, because you know why, if you keep this, then there will be channeling charge. So that's why they keep a certain height. Then again they collect this liquid, then again spray. That is, it has been seen that is the better way to do that. So characteristic of packing tower packing: larger surface area, uniform flow of gas and liquid should be there. So that is the, and high void volume, so that there will be low pressure drop, high mechanical strength and fouling resistance. So these are the best characteristics of the packing material. Now we will see the first packing, that is the racing diameter 6 to 100 millimeter, okay, 0.6 centimeter to 10 centimeter. So this is the diameter, and this is the ring, just nothing but one cylindrical application, that is called racing ring. So if you put this thing, so liquid will flow from this side and outside and inside also, and there will be, if liquid gas also flow like this, then there will be, you will get better. This is the first packing material. This is the same. Then second thing came lacing ring. So lacing ring is the same, that but they made one plate here inside. So if once you put this plate, then you are getting the better surface area. Your surface area for the master transfer is high. Then third thing is Berl Saddle. So, but it has been seen, if you keep this like this this geo, it has been seen that the mass transfer is high. Then Intalox saddle, it is the better one than that one, because it is designed in such a way so that when you put this packing material in this column, you know the contact between two packings will be very minimum, because but if it is minimum, that means no more void will be there. Then Tellerette. So if you see now, if you instead of making if you make like a tape type of thing, okay. So if you do like a tape type of thing, then it is you will get more sharp. But here the concept is very simple. How we will get the much surface area? So if I make a tape type thin type of thing, but if it highly resistive, it can withstand that whatever the load will be given. So I will go for this. Then another thing is called balding. If you see, that is the modification. Same thing, cylindrical, but then they made like this, cut it and put it inside. So there will be the surface area has increased enormously, and here the pressure drop also will be very less, because gas liquid can move. Then these are the random packing. Random packing means it has been each ring packing material, then they put it in a dump in this column. But now it is regular and structure packing, because then we feel that's ring thumb, but it is stick together, so it will come as a thing. So, and according to diameter, you put it you cannot dismantle it. Okay, this is the regular structure racing and other things. So what are the different thing? It will come like this. Okay, so if you take the history of packing, first generation packing is 1895 to 1950. Racing ring, barrel saddle, all these things were there. Second generation, folding interlock saddle. That is, you understand, around 50 years people use this only. Then 50 to 70, within 20, then it came that wall and interlock. Okay. Now then kept the net grid, because if you do like this in 1997 to 1990, up to 1990s, it is not very hard. So this type of thing is coming. If you see, if you instead of making this, if you make like this, then your surface area is high also. This thing. The fourth generation thing, it is coming like this, tape type of, and it is very low pressure drop and better mass transfer after late 1990s. Now what will be the next one? Next, you make the packing material in nano level. You understand why nano is very important nowadays. Everybody, nano means is nothing. You make the particle in nano range. If you make the particle in nano range, that means you will get the more surface. Okay, if you take the 1 gram, let's take brick. What is the surface area? Now, if you make it in nano level, then surface area will be huge. If you calculate the surface area of this nano level of 1 gram of pigs, it will be the half of a football ground, if you can make like this. So this is slowly the thing is coming. So thank you for your attention. Here we discuss some overview of two towers, two things. One is plate column, another is packed.